Good afternoon, David. Good afternoon, board that just left. Good afternoon, Ashley. Hang on, here we come back to good afternoon. Hi, Sarah. Awesome. Okay. Um,
Good
hi.
afternoon.
Oh, good afternoon, ABK. And there's okay. Hang on. We are okay. Good afternoon. He's gonna say it. He's gonna say top of the afternoon. Vocally say it. Say top of the afternoon. No, he's not. No,
Top
no.
of the afternoon, Professor.
Top of the afternoon. Thank you. That just changed my day. It just started my day. All right. Good after. Thank you. And the yellow, that means he's in a lot. Anyway, all right. I'm going to stop calling attention to people, except for the people that I'm calling attention to. Good afternoon, Dave. Hi, Sarah. Good afternoon, Chloe. Good afternoon, Gianna. Oh, and everyone see this community oriented of her. Oh, and there's Brianna also in yellow. Maybe in a lab. Maybe. Is that a lab? No, it's a classroom. Okay. Why am I? No. Okay. Okay. And more people are coming. I should not be calling attention to people. Um, I don't know why, actually. Oh, and there's another. Oh my God, are we setting video records today? We are setting video records. We're gonna get 10K again. Oh, there's Jalen. Yes. Okay. Okay. No, we're gonna start. We have math to do. So where was I? Good afternoon, Gianna. Good afternoon, Olsmail. Good afternoon, Jada. Good afternoon, Ashley. Good afternoon, 2D3D Steven. Good afternoon, Jasmine. Good afternoon, Diana. Good afternoon, Samuel. Book two. Sorry. Oh, good afternoon, Brianna. Well, we said that, but good afternoon. She double, yes, chat and video. Good afternoon, Brooke. Good afternoon, Jalen. Okay. And Nicholas is coming. Okay, we're going to start in a second. I got to bring the board back. And also bring the board back and give me 2 seconds. I know this is what happens when I'm on time. We're already late. Give me 2 seconds, please. Okay, more people come. All right. Actually, I do need. All right. Oh, people have media. Good afternoon, Nicholas. Awesome. All right. Actually, everybody give me two. I'm having two technical things that are going on. Oh, and there goes my board again. Hold on. Um, okay. Okay. Almost there. Sorry. Don't know what. Almost there. Did I lose the board again? I think I lost the board again. Okay. Okay, we're going to so sorry. Bear with me for like one more minute. I do want to get down to business. Actually, I don't even think there's announcements. I think I just have to fix two technical problems here. If there are announcements I'm forgetting or questions, like put them in the chat, please. And I know some of you I owe some. I know March 1st. Let me put it this way. I know March 1st is just around the corner. I'm very aware, and it will all happen in time. And if you don't know what I'm talking, don't worry about it. But if I'm talking to you, I am talking to you, and I know that I'm talking to people in this room. Okay, but give me a second. Oh, Um, is okay. Let's see. All right, so the word, okay. Yeah, let's get to business. What's on the board right now is what I want to get to today, even though, again, in some ways you've seen it many times. In a way, you've seen it already in the lab and in the homework, but okay, forget again, I'm just going to get right to it. But if there's any issues of any kind, please let me know in the chat. This is all. Okay. Okay. Okay, let me just, oh, something's in the chat. It might be hello, but it might be really important. Okay, no problem. Thank you. No problem. Direct chat person. Gotcha. Okay. Now, here's the deal. It seems like, yeah, I'm going to question 9 on homework 1B, which seems like a million years ago that it was assigned. I mean, it was, but let me tell you right now, like specifically question 9 from homework 1B was, when t equals 1, what's x? Like that is specifically what the homework question was. And by the way, I think the answer was approximately 0.116 meters. You know, if anybody's like tracking that, or if that brings you any psychological closure to know. But one of the reasons we took so long to get to question 9 in the lectures, and one of the reasons that we have like a whole homework assignment right after that in some ways the first 3 pages of which, I mean, or so, are all different perturbations and perspectives on this one question, is because the question that sounds particular and specific, it just sounds like at t equals 1, what's x? The question is really a much larger question than that. The question is a general question. The question of number 9, homework 1B, and the question that in fact has been underlying like the last 3 labs you did and the next lab you're going to do, the real question is, given f equals negative kx, what is x as a function of t? Okay, that's what we're really asking. And in English terms, let me back up on that. Okay, we're asking what is X as a function of T? And I submit to you that in a way, that's what we're always asking in physics, or some version of that is what we're always asking in physics. Physics is about stuff moving through space and time, right? In some sense, every question that we ever face in physics, and I'm really not exaggerating. I mean, all there is in physics is masses in space. All there is stuff of some kind, mass or energy or something, particles or information in space and time. So all there is, in other words, is kilograms, seconds, and meters in a way. So all we're ever asking is, if you name the time, can I name the space? Or maybe sometimes the other way around. If you name the space, can I name the time at which some bit of particular matter or some bit of information will be at those coordinates? You name the time coordinate, can I name the space coordinate? You name the space coordinate, can I name the time coordinate? That's physics, really, at any level. The thing that makes one chapter of physics different from another, or one entire curriculum of physics different from another, or blah, 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 or one investigation of physics different from another, is the conditions that we specify and impose on that question. Okay, that's what, and here, what we're looking at in this big chapter with which we've begun, Physics 204, the big condition that we're looking at is the elastic force, the Hooke's law force, F equals negative kx. Really, in broader terms, we're looking at a situation where the extent to which something is pulled or pushed is linearly dependent on where it is, right? That's what F equals negative kx really means in broad terms. What elasticity really means in broad terms is that something is being pulled from where it is in a manner that depends on where it is, right? F equals negative kx. So what we're really asking in question 9, on the one hand, we're asking a really fair question. Where is the object at a certain moment in time? And we're just saying, given this condition, that wherever it is at any given moment of time determines how hard it's being pulled toward equilibrium, right? So it's like a really general, but in a way, really like fair question. It's almost surprising that all of the questions we answered on the sheet and all the questions in the first 2 labs in some ways didn't land on this. Like, how are we doing all this physics for a month and not asking this question? And the answer is all the physics we were doing for a month, all the first questions on the sheet and everything, all of them had to do with the relationship between where the object was and how fast it was going. Or put another way, had to do with the relationship between how fast it was going, instantaneous speed, as a function of where it was. They were all speed spot mappings, correspondences, relations. And that's not a coincidence, because what we've been looking at is harmonic oscillation. We've been looking at energy conservation, and energy conservation is all about a relationship between how fast you're moving versus where you are. Now we're finally trying to bring time into the situation. We're trying to ask, okay, well, where are you as a function of time? And it should be straightforward. We're just going to do what we always do. Look at F net equals ma, right? So we say, all right, we know that F equals negative kx. We, in this case of a mass on a spring, and we know that the sum of all the forces always produces the acceleration, right? We know, like, the first statement is specific. So these are the GDPs, so to speak. One is specific to this problem, and one is true in physics in general, right? So we put them together, but then we say, all right, the only force acting in this situation, the only force acting is the elastic force. Therefore, it is the net force. It is the sum of all the forces, right? So we go like this. I'm just quickly reviewing, in effect, the math that we set up at the end of last class, last Wednesday. So we say this, hello, okay. So we say that. Then we say, okay, so negative kx equals ma, like we're trying to solve for x as a function of t. right? So then we say, okay, we remember, oh, A, after all, A, by definition, instantaneous, not average A, not average acceleration, but instantaneous acceleration, acceleration at a point in space and time. By definition, that means the instantaneous rate of change of the instantaneous rate of change of position with respect to time, right? I mean, acceleration is the derivative of velocity. Velocity is the derivative of position. So we know that by definition, A is the second derivative of position with respect to time. So we substitute in, we say, fine, negative kx equals m times g2x gt. I'm just substituting in, right? Okay, and then I'm rearranging slightly just to make this clean and easier to look at. So I say, okay, what I'm doing is typical physics taste, typical physics style of packaging all of the constants together, putting them out in front next to the variable, the dependent. Now let's be really clear, right? The dependent variable. Sorry, I've been noticing, looking back at these, that the red really never shows up on your side. You've been very polite in sort of not mentioning that, but so this is the independent no, it's not. This is the dependent variable x. But t is the independent variable. So what we said last time is, at some level, we're just about there. We now have a statement that has the correct content. That is, the only variables in this statement are x and t. Everything else in this statement is a constant. So that's the good news, because we are looking for x as a function of t. But the bad news is that we're looking for x as a function of t. We're looking for a straightforward rule where you plug in t and as an input, and I give you x as an output. That's not the way this is being phrased or packaged, right? The information is all there. Somehow x and t are being related to each other. But what this thing says is, and I know I mentioned this last time, this thing says, oh, I can tell you how x and t are related. They're related like this. The rate of change of x with respect to t is some function of x. Now that is, as I mentioned Sorry. Okay, we've been building to this for weeks because this is a big deal. It is a big enough deal that I have to teach it. What we're up to now, and I know you've been playing with this in the lab and all that, but let me stop now as your lecture instructor or whatever and say what we've arrived at in the material is something called a differential equation. It is not just an equation that has a derivative in it. It is something called a differential equation. I want to be very specific about that before I go, because it's like a big, in some ways, the study of, physically, what physics is all about is you name the time, I name the space. But then I said all the different branches of physics or all the different topics of physics distinguish one another by imposing different conditions on that question. The conditions, the specific conditions that define a specific topic of physics, whether it's from the 17th century or the 21st century or the, what year are we in now? Or the 21st century, right? The different topics that are distinguished by different constraints on the larger question, where is something when, really are expressed mathematically as different differential equations. Differential equations really are the mathematics that drive the study of physics, like really. Now I need to unpack this in some kind of like real systematic way, or some kind of real systematic way for you. Before I do that, and again, I know you've been playing with it already in the lab, and that's as it should be. And you've been playing with it in the homework. That's as it should be. That is how the history of physics and math and differential equations progressed. That's how the human mind works. We play with things and we experiment, and then we eventually come to sort of clean up resolution. So that's all as it should be, but I do want to start giving you the cleaned up resolution now. Let me say, before I go any further, notice the volume in my voice. It is not out of anger, it is out of intensity. Let me say that we are about to, at some level, investigate this notion of a differential equation. It is a calculus thing. There are courses in the world called differential equations. There are courses called partial differential equations. None of those courses was a prerequisite for this course. Let me say that again. You were not expected or required to have taken any differential equations before this course. You were also not required to take Physics 204 before this course. What do I mean? I mean, you were not expected to have taken Physics 204 before this course. You're expected to learn Physics 204 in this course. Same thing with differential equations. I'm not expecting you to have them coming in. I'm expecting you to have enough math and physics coming in that together we can embrace and attack some aspects of differential equations together. We are going to learn what we need to learn about differential equations to do this material. It's not a prerequisite, it's a requisite. Okay, just to be clear. And I think it will work fine. I mean, it always does work fine for everybody, as long as you know that, as long as you relax your mind and say, and don't think of anything I'm about to say as something you were already supposed to know. Think of it as things that we are learning now. Now, would it help if you already had a little bit of knowledge of derivatives and of integrals? Yes, which is why technically you were required to take those, but more specifically, why we reviewed them or recalled them or refreshed them for the last few weeks, so we can get to this level of calculus. Okay, which we'll all do together in as many drafts or as many study sessions as it takes. So the first thing I want to say is a differential equation is not the same thing as just any equation that has a derivative in it. Let me show you what I mean. Okay, so first of all, a differential equation certainly is an equation that has a derivative in it, but it means something more specific than that. Okay, not all equations that have derivatives in them are differential equations, not in a meaningful sense anyway. So let me well, I'll tell you, I mean, the punchline is that a differential equation is precisely what we just said a second ago. What I'm going to unpack for you now, but let me be clear. What makes this thing that we're about to solve, this thing, okay, this thing is a differential equation. It happens to be a second order differential equation. I mean, it happens to be a differential equation that involves a second derivative. That makes it even fancier. Honestly, that makes it even a little bit harder to solve. But it's the first one we're going to deal with in this course because it's the first one that comes up in the study of physics. But what makes it a differential equation, and not just an equation with derivatives in it, what makes it a differential equation is precisely what's written on the next page, that the derivative of some dependent variable with respect to some independent variable is being expressed as a function, not of the independent variable, but of the dependent variable. That is a key, huge distinction. Let me say that a different way, or in fact, let me back up on that for a minute. I look at the left side here. I look at the notation d2x dt squared. I immediately know just from notation that t is being treated as an independent variable and x is being treated as a dependent variable simply because the t is in the denominator and the x is in the numerator. Okay, like remember, and don't be bogged down in the fact that this happens to be a second derivative. That is life. It is, because that's what the physics is telling us. But don't even worry about that for a second. Just look at the fact that x is in the top and t is in the bottom. Remember, a derivative is like rise per run instantaneously. Whatever is the rise of the function, this axis, is what we view as the dependent variable, or in other words, like, in a way, if you like, the effect. Whereas whatever's in this axis, the run, is what we view as the independent variable, or in a way, very loosely speaking, the cause, right? This drives this in any function that we ever look at in math or physics, right? So, and that's why our notation preserves that. Whatever's in the top of a derivative is understood to be the dependent. Whatever's in the bottom is understood to be the independent. This statement says the rate of change of x with respect to t is equal to negative k over m, is equal to some function, some linear function in this case, some function of x.
all of my verbiage here, for which I'm sort of not apologizing, all of my verbiage here is to tell you that the fact that the right side has an X in it rather than a T makes an enormous world of difference. And that's what I'm going to try to unpack for you now in a mathematical example. And I'm going to try to keep saying in different ways in English. It makes all the difference. We are saying that the rate at which some effect changes with respect to cause depends not on the cause, but on the effect itself. If that makes you bump slightly, if you're like, wait, what did he just say? Or wait, is that what he meant to say? Or wait, what? Then you're with me. If that makes, because we are saying something self-referential here. And I'm going to try to show you that in the math and the English and the physics. I'm saying that the way in which effect depends on cause, or the rate at which effect changes with respect to cause is actually in effect of an output of, not the input, but the output itself. There's something like going on here, which in fact, technically, we call feedback. And if you're there's like a little bit of a paradox, a little bit of a two mirrors facing each other kind of situation here. If you're seeing that at all, if you even thought you were with me, then you got a little confused with what I just said, you probably are very with me, because what I'm saying is a little bit confusing. But I'm saying, and I'm going to show you an example now, that if there were a T on the right side of this, then that would be an equation with derivatives in it for sure. It'd be saying the rate of change of X with respect to T is dependent on T. It would be like saying acceleration changes by 42 meters per second squared every second. It would be interesting, but it wouldn't be a big problem. We would just do derivatives backwards to solve it. We would integrate to solve it. But that's not right. And in fact, whether we thought about it in calculus terms or not, that's what we were always doing in physics 1. We would say things like velocity is changing 9.8 meters per second every second, right? So we would give some rule about the rate of change of velocity, and we'd work backwards and say, oh, well, then I guess acceleration is 9.8 or whatever meters per second squared. Oh, then I guess X equals 1F AT squared plus V naught T. We could do all of that because we were being given rules about V or A that were all dependent on T, which was what everything was supposed to depend on because it was the independent variable. Now we're saying this feedbacky thing. Okay, and I'm getting myself too bogged down, but I said this on Wednesday. We're now saying, oh, you want to know where something is? Well, no problem. I'm a physicist. Just tell me what its rate of acceleration is, and I'll tell you where it is. But then this equation is saying the rate of acceleration depends on where it is. Not what time it is, but where it is. That is circular at some level. It's weird at some level. So it actually invites a higher level of mathematics to unpack. It's even actually surprising or interesting that it can be unpacked at all. Okay, so this is, I am saying, if you want to write anything down in your notes, I'm saying a differential equation means necessarily, it means this. It means that the derivative of some dependent variable, like where you're assuming that X is some function of T, it means the derivative of X. Now, in this case, it's actually the second derivative. That's okay. If any kind of derivative of X with respect to T is being expressed not as a function of T, but as a function of X itself, then it's a differential equation. And that just means it takes a different kind of thought to unravel. Okay. Now in this case, it's a second derivative that's being expressed as a function of X. The second derivative of X with respect to T is a negative sign times a constant K over M times X. So it's not a hard function. It's a linear function. If I put the derivative on the y-axis or the second derivative, and I plotted the X on the x-axis, I get a straight line. Like, it's not a hard function. What's hard is the fact that it's a function of the dependent variable, not of the independent variable, okay? That's the differential equation we have here. It's technically called a second order differential equation. It's technically called a second order linear differential equation. And since it's like a y equals mx plus b situation, we call it linear. But since there's no b at all, there's no plus b to like the y-intercept is 0, 0, nothing. We actually technically, if you care, if you're tracking this, technically, this first differential equation that we're ever getting in this course or people ever got in life, in a way, is a technically called a second order linear homogeneous differential equation, if you care. And there's all different types in life, but this is the one that we're landing at because the physics is bringing us there. Okay. So let me back up. Sorry. Cool. Hold on. Yeah. Sure. Yeah. No, great. Someone in the direct chat. Okay, I'm not going to say names because it's direct chat, but someone in the direct chat who definitely should submit for points, and I'm very pleased that he or she is doing this. Someone in the direct chat is saying, sorry, Professor, can you repeat the overall meaning of differential equation one more time? I want to make sure I get it. That's a very fair question. Yes. Well, the good news is it's what this board says right here, but I will say it again. Yes, happily. A differential equation is one in which the derivative of some dependent variable is being expressed as a function of the dependent variable, as opposed to the independent variable. Like literally what's written here is what I'm saying is the definition. A differential equation is where like you have the derivative of x with respect to t, or the derivative of y with respect to x. Well, I'll just say it again. I know you just want to read. A differential equation is an equation in which some derivative is being expressed, is being set equal to a function of the dependent variable, of the rise variable, as opposed to the run variable. That's what makes it a differential equation. I don't know. And person who asked in direct chat, just tell me, please do tell me if I should say that one more time. I'm happy because it is important. You're right. Or tell me if you got it, or in the direct chat if you can, or if awesome. And now you can submit for 400,000 points. Okay. And again, and people, please, I know I'm screaming, not because I'm upset at all. I mean, I'm intense but this is like a really big topic, and and it's actually really gratifying for me to get to teach it to you. Honestly, like I love showing people this, and I think you will get it when you're done, or you'll get what we need to get out of it. But like I remember the years and years that I did not get this, and I took courses and courses. I took courses called differential equations because I had to, and I took courses called partial differential equations because I had to. And I'm not saying I did badly in them or whatever. I mean, sometimes I did actually, but what I'm really just saying is like it took me. I never really understood why. Like there were all these separate courses. Like I felt by the time I got to these courses, I was like, I've done a million equations that have derivatives in them. Like, what is the big deal? Like, what is special? And what it felt like to me when I took those courses is, okay, we're just doing like really, really hard equations with derivatives in it. I just thought they were called those. I thought they were separate courses because it just happened that the problems we were doing were like so hard. I mean, which they were, but no, the thing that escaped me forever until is that the deal, the importance, the reason we need a whole set of techniques is that a derivative is being set equal to its dependent rather than its independent. And let me just also say to you all, if I'm going to make a big deal of this, which I am, I want you to know again, I'm not expecting that you already knew this coming in. This is one of those times where I think it's much easier to learn the math by having the physics first. And God, heaven forbid, or quark willing, if any of you ever do go on in math and take courses called differential equations, I think you'll have a much easier time of it for this. But I'll really say this too, last plug, and then I'm going to show you last negotiating after the close on my part. What we're about to talk about right now is super relevant to PChem and instrumental, but particularly PChem. If you haven't, I mean, the number of people that have come back to me feeling like they had a clue in PChem because of this, it's one of the most gratifying things to me. And that doesn't happen in all classes or anything, but everything I'm saying now is to set you up for PChem, which means secretly I'm trying to set you up for mini quantum physics. Because at the heart of quantum physics is this thing called the Schrodinger equation, which you may have heard about in chemistry as well. The Schrodinger equation seems so arcane and so crazy and so hard to so many of us, but partly because it's a differential equation. Once one understands that it's a differential equation, it's a lot easier to make inroads into it anyway. So this is, I'm not just spinning your wheels, I promise. And I'm not expecting you to know what I'm saying before I say it, but I am expecting you to be with me while I say it. Okay, enough build up. So, okay. So first, I'm going to show you. So this is all in an attempt to give context to it. Well, no, okay, I'm going to lose people. Let me first give you like an answer. Yeah, I'm going to first give you an answer to this differential equation so I don't lose everybody, or a solution. And then I'll back up and show why like that's actually deep or whatever. So our differential equation here. Right, this is our differential equation. So what it says mathematically is that we're okay, it's a differential equation. It is not an answer, it's a question. All differential equations pose a question. And right, sometimes we're used to in science thinking like when you finally have an equation, then you've an answer to your question, you're something to plug into, and you're done. It's the reverse here. This equation prompts the question, sets up the question. The question, to remind you, the question is, given this nature of rates of change, the question is, what is f(x) as a function of t, right? We're looking for some mapping, some rule that treats t as the independent variable and treats x as the dependent variable. We're looking for a rule or a mapping or a correspondence between an equation. We're looking for an expression that links x to t such that we want an x as a function of t such that the second derivative of x with respect to t equals the constant k over the constant m times -1, all times x itself, right? So when we find the correct x as a function of t, that will be what is known as a solution to this differential equation. To solve this differential equation, we don't get a number, we get an expression for x as related to t, right? Okay, once we and remember again, functions are number in, number out. Operations are functions in, functions out, right? The differential equation is saying when you operate on a certain function this way, you get back the function times a constant times -1, right? That's what this thing is saying. It's saying you take the rate of change of x, that's the left side, you'll get back x itself, but times a constant times -1, right? So in order to solve this, we're not looking for a number. we're looking for the function of x that behaves according to this differential equation. So when we find an x that meets this, that satisfies this condition, we will have found a solution to this differential equation. That's called solving the differential equation. Really, what I mean, and if you're not careful, if you're not following all this, it looks just like algebra or something. What we're saying is this is an equation that needs to be solved. To solve it means unpacking it, unraveling it, so we finally have x as an expression of t. And that will just look like another equation to all of us. Like if you don't know what's going on, it just looks like two different random equations. But when we get an x that works, that will be called a solution. We will have solved this differential equation. Now, okay. Well, hello, what just happened? Besides, I started singing for no reason. Wait, okay. Okay, so what I'm going to do to show you what it means to satisfy this differential equation is I'm going to start by giving you an example of a function that has the proper form x dependent on t. But I'm going to give you an example. I'm going to show you an example of an x equals f of t, which does not satisfy this differential equation. I'm going to start by showing you a counterexample, just so you can see the meaning of what it is that we're looking for. Oh wait, no, not okay, sorry. Okay, so I'm on purpose starting off with a counterexample so that you can see the point of what something that doesn't work, so that you can see what we're looking for that does work. So for example, okay, let's say this function, like it's familiar, x equals 1/2, like we used to say x equals 1/2 at squared plus v naught t. Now I'm trying to be sort of smart. I'm realizing that right now we're talking about springs and masses and all that. So right now we're not talking about constants known as a or v naught or anything. The constants that we have right now in our life seem to be the constants k and m. So I'm trying to be clever. I'm saying, well, we had this old equation that always used to work with, well, that often used to work for us in physics 1. We had an old equation where t was the input, x was the output. So it fit. And if we just adjust it and like put in the appropriate constants, it seems like this would not be an unreasonable guess. And it's not an unreasonable guess. Like, just to be clear, So this is a conjecture. I'm conjecturing this possibility as a solution to the differential equation. And I'm conjecturing it because not crazily. Like this is based on experience and it has all the right ingredients. Like it is an X as a function of T and it does have constants K and M. Like it's not at all a crazy conjecture, right? And I'm thinking, I wonder if this is the kind of function that I'm looking for that would satisfy my differential equation. And it'd be great if it was, because I know how to use this equation. I know how to plug in T. And by the way, if this is right, then I could answer question 9 from sheet 1. I could plug in some value of T, like 1 second, square, multiply by K, which is 200, divide by 2, which is 100, and then multiply that, add, and then get an X and get an answer. But how do I know? How do I know whether this does or does not satisfy the differential equation? Well, I can test it. Differential equations are not always easy. They're not always possible to solve. They're not always easy to solve or to guess, but they're always easy to check possible solutions. I'll show what I mean. Okay, let me be clear. A differential equation is a kind of backwards kind of question. It's like Jeopardy. A differential equation says, I've got this function for which when you differentiate it, you get this thing over here. What is the function, right? A differential equation is asking something kind of backwards. It's not saying, here's a function, do something to it. That's not what, right? A differential equation doesn't say, here's the function, now take a derivative or take 2. It says, here's a function for which when you take, in this case, 2 derivatives, something happens. Here's, in our case, here's a function which when you take 2 derivatives of it, you get back the original function times K over M times a negative sign. That's literally what our thing is saying, right? In English, what we're really saying is when we have a seemingly simple system of a mass going back and forth on a spring, and seemingly simple in the sense that, oh, wherever the mass is, it's pulled by a force, which is linearly dependent on where the mass is. Like it's a straight line, like it is as straightforward in a way as it could be. We're saying, look, the force on this thing, and really, therefore, the acceleration of this thing is directly proportional to where the thing is. It's just direct proportionality. Could be more straightforward. But the catch is that the direct proportionality is that the acceleration is not directly proportional to time. It's directly proportional to position. And we're trying to find out position, right? So our differential equation says the rate of change of position is the following function of position. So we want some position function. We want some rule. Maybe it's the one above. Maybe we're about to find out. We want some position rule such that when we take 2 derivatives of it, we get back itself. We get, right? We want d2x over dt squared to equal x itself times k over m times -1. That's what we want. So what do? I don't know how we can come up with guesses. We come up with guesses from our education, from our background, from our experience, like literally. So I just came up with one. I just came up with a guess, a conjecture. It's not a stupid conjecture, but it is a conjecture. I didn't figure it out. I guessed it, but now I can test it. And this is how differential equation solving often works. It often works by conjecture and verify, i.e. guess and check, just like integration does often. I've got this guess, this conjecture, x equals 1f kt squared plus mt. It's just a guess. I don't know if it's true or not, but it's an educated guess. So in order to check it, I differentiate. I take a derivative. I take the derivative of this with respect to t. In fact, I take it 2 times to see what's going to happen, to see if I get back itself times k over m times a negative sign, right? And I'm going to say again, I'm going to turn the page and I'm going to do it, but I want to emphasize this. Coming up with solutions to differential equations is an art. It is not an algorithmic science. It is an art, just like integrating. Like differentiating is always an algorithm. It's always a procedure. Going backwards with like integrals, right, is a whole bunch of techniques and experiences and tools that you learn and you try over time. And then you can always check, but you don't always know what you're doing until you land, right? With integration, integration is fundamentally more of an art than is the science of differentiating. Well, this is even more so. This is puzzle solving. There's different techniques for coming up with original thoughts, but then whenever we have a thought, however we got it, we can always find out if the thought is right or wrong by going backwards and differentiating. So I'm going to do that now. I'm going to say, well, we're supposing x equals 1/2 k t squared plus mt, right? Then I'm going to take one, and we're trying to see whether this x satisfies, solves, fits, is consistent with. We're trying to see whether it satisfies this. So we take one derivative. I'm going to take one derivative. Let's see. Right. One derivative of x with respect to t. So I'm going to differentiate. And please notice, I'm not differentiating the differential equation. That's already differentiated. I'm differentiating. I'm taking a derivative of my guess. I'm differentiating the x of t expression up there. So I'm going to take a derivative of it. I'm going to do, like, t is the independent variable, x is the dependent variable. In fact, everything else is a constant. In fact, okay, wait, should I do? I kind of do it. Yeah, I'm going to ask you in the chat. I'll wait till I get 3 people in the direct chat, please. In the direct chat, not the public chat, please. I'm going to wait till I get 3 answers in the direct chat. Can you tell me, please, what is the first derivative? And I'm going to ask you again for the second derivative in a moment too. If you're following me, you'll see we have to take 2 derivatives to check this thing out. But can someone please? Can all of you please, in the direct chat, and I'll wait till I get the end, in the direct chat, can you please tell me what is dx dt, assuming that x of t is this thing up here? Please tell me in the direct, I know we've got 17 minutes, this is worth it to me. Please tell me what is d, and I'm not asking, like, I'm asking you to clear your brain, just look at that x expression. X is the dependent variable, t is the independent variable. So it's like treat x as like y and treat t as like x. Everything else is a constant. Everything else is treated as a number. Tell me the first derivative of that expression. Don't worry about differential equations. Just tell me the derivative of it, like in blank slate. But I will wait till I get 3 answers in the direct chat. Or you can write in the direct chat, sorry, I've lost you. I don't understand what the question is. Or sorry, I lost you 8 months ago. I don't even know what college I'm in or whatever. But please tell me the derivative of x with respect to t. Oh, that's one. Awesome. Thank you. Awesome. Okay. I'm going to say there's one person in the direct chat so far. So if I'm talking to you, I mean, then first of all, thank you for, it's you went public chat. Oh my God, wait. So I'm not going to say if it's right or wrong, but I would no, and I appreciate, that's really gutsy. I'm not going to say if it's right or wrong because it's public. I want 2 more people to go. But I am going to say it's awesome that she put something in the chat, and no, it's okay. It's totally okay. And it's all to your, and you should definitely submit for 1,000,000 points. And I appreciate the guts, really. And I'm going to say to everybody, I will definitely say this. I'm going to wait for 2 more answers, whether they're private or public. But the thing what Jalen awesomely did put in the chat, first of all, she's totally paying attention. There's no question. She definitely gave an answer to my question. Like, she definitely gave the thing I'm looking for, the kind of thing I'm looking for, which is she gave on the right side some kind of function of t. The only thing on her right side of her equation is t's and constants. That's what I'm looking for. I'm not saying if she's right or wrong. And frankly, I don't care if you think she's right or wrong. I want to see 2 other people do something with this. Just prove you're paying attention, even if you copy her, like whatever. Like, we got to be together on this, because if we're going to do differential equations, we got to at least know derivatives. So we got 1 person. I'm waiting. I'm going to change the view on the screen so I can like really yell at people. Did I say yell? I'm not yelling. It's out of love. But also, come on, Jalen. I mean, what does it mean that the 1 person that participated has known me for less time than everybody else in the room? That either means that she's the only person left who still has faith in this class. No, guys, I need 2 other participants. I need it. I'm going to die. I'm not going to die. I'm going to dye my hair blue. I'm waiting for a derivative. See, this is worrying me. I need a derivative of the expression in the top right. Whether you agree with Jalen or disagree. Oh, I just saw one in direct chat. Awesome. That's 2 people. Awesome direct chat person. And since you're in the direct chat, now people are going crazy. Okay. Awesome. Now there's a lot in the direct chat. Thank you. Phew. Okay, wait. No, okay. And now there's even comments in the direct chat. No, you are doing the right thing. If you are taking the derivative of the expression in the top right, you are doing the right thing. And I will say this right now. One of you, okay, this is great. Thank you. I now feel like things are happening. Okay. And also, if you're being honest, and I'm being honest, this is also helping me and making me realize like we might need a little review, like we all might need to review a little bit derivatives and integrals and stuff like that. I will tell you, I've gotten a lot of correct answers in the direct chat. I've gotten some that are not as correct, but they're all please submit these for points. I'm going to tell you right now. Oh, great. Now things are really happening. Okay. This is great. Thank you. So here's the deal again. I'm asking you to differentiate the thing in the top right. I'm asking you to take the derivative of the thing in the top right. I'm not asking you to take the integral. To be honest, a couple of you actually took like the antiderivative. A couple of you went backwards, maybe just because you got the rules confused or but I'm going to tell you, oh, cool. Okay, fair enough. Now people are like, oh, and anybody who says they agree or disagree with Jalen also gets points for multiplayer co-op. That's good. So at least 1 person just did that, like mentioned Jalen by name. Thank you. Okay, so now I think people are with me. I would love to respond to each one of you by typing in direct chat. I'm not going to do that because I'm watching the clock, but I again commend all of you. And really, those of you who are going to now in a minute find out that maybe you weren't perfectly right. Like, honestly, in some ways, I'm commending you even more. Do not shy away from this just because you think you're not sure. Like all of you that are at least showing that you're with me with what's going on, it's helping a lot. And if all of you put in a wrong answer in direct chat, I would know that I've got to teach this better, right? It's as much a reflection on what I need to do as it is on you guys. So do not be embarrassed by wrong answers. Be embarrassed if you are not paying attention at all. But then you didn't hear me say that, so you can't be embarrassed. So what I'm going to say is, if I'm asking you to differentiate the top right expression, I'm asking you to take 1 derivative with respect to t. That means you do the power rule in the forward direction. And yes, I totally agree with Jalen. What Jalen put in the public chat is totally right. And those of you who agreed with her are totally right. Those of you who put answers that maybe like had t cubed or something, you're not crazy. You're not in the wrong place. Don't transfer, don't drop the class. But if you put something like t to the 3rd, that means you're thinking antiderivative. You're going in the sort of backwards direction. Okay, so you're like either a step ahead of me or something. Right now, we're just checking that possible expression by differentiating it. So we should get KT plus M, like that is correct. And if you put a plus C or something in your answer, which a couple of you did, you're also thinking about integration, not differentiation. And just keep staying with me for the next couple of classes. If you're still confused, if it was just a gaffe, no big deal. But if you're legitimately confused about differentiating versus integration, you may want to talk to me directly. No, and so someone who said that they think it's KT plus M, but they're not sure if they did it correctly. No, they are doing it correctly. Now, here, I'm going to go on. So first of all, thank you, all of you who participated. You should submit for points. Hopefully you're seeing you are getting those points. And definitely thank you, Jalen. You didn't do anything wrong. I just wanted to spare people and you were right. I mean, you were right and you were right, Jalen. And anybody who's, but now we're going to go a step. So what does this mean? So far, what we're saying is, we're saying if X equals 1/2 KT squared plus MT. Now notice, those of you who have even tried homework 2 should be seeing something familiar going on here. We're doing the thinking that is being asked of you in homework number 2. We're trying solutions and seeing if they work. Don't worry about where I got these possible solutions. I got them from past experience in physics. You could have guessed this also. It's just a guess. But I'm trying to see if the guess is correct by taking derivatives. I took a derivative and I found, by doing the power rule, and I found, or Jalen and others found this, right? K and M are just constants. Now, what does that prove? That proves nothing besides the fact that Jalen and others are totally with me. In order to prove whether my guess is right or not, I have to go another step now. I have to go to the second derivative. Why do I have to go to the second derivative? Because my differential equation said that the second derivative of X with respect to T equals some blah, blah, blah expression of X. So I got to find, so I'm looking for the X that satisfies that. This is reverse engineering, so to speak. This is like that game show Jeopardy. It's confusing to people or can be. It's not meant to be, but it can be confusing and jostling to people, especially if you've just sort of started getting comfortable with calculus. We are kind of asking you to do calculus backwards now. And we're not asking you that to give you a hard time. We're asking you that because that's what the physics is presenting to us. It's saying we've got some kind of acceleration that depends on position rather than on time. That is a bass-ackwards kind of phenomenon to see. And yet it's a totally simple, customary, familiar, prevalent phenomenon called springs, called oscillation, and called pendulums. So it's inviting us to find X as a function of T such that its second derivative bears a certain relation to X. So I took the first derivative. Now I'm going to take the second derivative. I'm going to take the risk. I'm going to think that now, because I'm yelling so much and because I got all this participation, I think a bunch of you are with me now. I'm going to ask very quickly. Believe me, I'm watching the clock. I'm going to ask very quickly in the private chat this time, in the private chat, can you tell me the second derivative? In other words, please differentiate this expression with respect to T. And I think this will be fast. If you think it's sort of simple or sort of short, you're correct. I'm not trying to intimidate you, but can I quickly get some participation in the direct chat for what the derivative of that awesome direct chat person that just went? I'm going to wait till I get at least 3. There's only 1 right now. So if you put it, I'm talking to you, and yes, you're correct. That's awesome. Can I get 2 more in the direct chat, please? I sound like an auctioneer. Can I get 2? I want the derivative of the right idea person who just went right idea. I think you just sort of typoed yourself. Like you did. Look, remember T, everybody remember T is the variable. K and M are the constants. There's been 2 people in the direct chat, and the second person who just went, I want that person to go again. Yes. Okay. Awesome. 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 I had a feeling it was okay. So I'm waiting. That's awesome. So I'm waiting for 1 more person in the direct chat. I'm going to do it like this all the time. This feels like, I don't know what, but I want 1 more person in the direct chat to tell me the derivative with respect to T of KT plus M. Think of it as, if I gave you the expression 4x plus 3 equals y, and I wanted dy dx, what would you tell me? It's just that, and this is what we want to get used to in physics. I'm telling you, the numbers are going to disappear from physics. It's all about letters now. And it's about translating everything you ever knew in math about y as a function of x to whatever variables we have in physics. T is the independent variable. X is the dependent variable. I want 1 more person in the direct chat to tell me what is the derivative of that boxed expression. Yeah, that's funny. Direct chat person. Yeah, we're going once. Yes, Yes, that is awesome. Last direct. Okay, so the three people that went in direct chat, if you went in direct chat, you are correct, and I'm proud of you. And I'm yes. So it's this. And by the way, if four people, awesome, yes. And now, and by the way, those of you like, if you're just bored, you're just bored. If you're just distracted, you're just distracted. Like, I understand that it's life, but I will tell you this: if you are paying attention to me, and you're like a little bit like not sure if you're following this, then take this as a, I mean, physics is getting very calculus-y now. You want to know your fundamentals of calculus, partly because you took them before, but partly because I think, sort of reviewed them in the last couple weeks. I'm not saying that disparagingly, but I'm saying it as a cautionary statement that, yes, we're about to have just enough comfort with calculus to be able to do it sort of backwards. That's what's happening here. So what I'm saying is this now to everybody, and I know we have 5 minutes left. First of all, if you did follow these derivatives, good. I'm totally pumped for you and with you. And if you didn't, there's still totally hope. Don't think I'm not saying that. I'm just saying know where you're at. So this K is the second derivative of X with T. But notice this. What I've just learned by doing all that, and I think it's worth it. What we've just shown is that X equals 1/2 KT squared plus MT is a valid function of T. It does treat K and M as constants and T as the independent variable. But what we just showed is that that is not the answer we're looking for. And that wasn't a waste of time. That wasn't a fool's errand. But by checking, see, we were looking, we wanted the second derivative of X with respect to T to equal K over M, negative K over M, times X itself. We wanted some expression of X such that when we took two derivatives of it, we got back the original expression. That's what we're looking for. That's not what happened. We got and I'm not saying that was wrong. I'm saying it showed that our check, it was a successful check that showed that our conjecture was wrong, i.e., in some situations, X might equal 1/2 KX squared or something, but not in this situation, is not a solution. With 2 minutes left, I'm going to say to you, and then we'll do this more on Wednesday, right? But now, again, I'm not showing you where I'm getting these guesses from yet. Truthfully, that's what the labs are for. The labs were to show you where to get these guesses from. I'll explain that more on Wednesday. And that's how physics as a science, as opposed to a pure mathematics, works, is we play around in the lab and then we get groundings for things that we have to guess as solutions to differential equations. But I'm saying now, with 1.5 minutes left, if from the lab, if we think, wait, we need something whose position is related to its time in the manner that this differential equation is asking. If we think about the lab, we saw something going back and forth and back and forth. We saw masses on springs going back and forth in time in a cosinusoidal fashion. If we were to guess X equals X naught cosine, say, this. Now, I know I said this on Wednesday, but I'm just saying that if we were to guess something like that, and I'll explain in more detail exactly why I knew to put the square root of K over M and blah, blah, blah. But if we were to guess that with 1 minute left, if we take the derivative of that, and I'll do it quickly because I know we're running out of time. If we take one derivative of this, well, I know that the derivative of cosine is negative sine, right? Sorry. And I know chain rule says that I should then, I'm doing this fast because I know it's, oops, sorry. chain rule says a derivative of a function, I'm going to write this more. I'm going to explain the chain rule on Wednesday. But if you remember the chain rule, it says you take out the derivative of the inner function and multiply by the whole thing. And if I do that one more time, I get negative, and I know the time, I get negative k over m x naught cosine of this, right? The derivative of cosine is negative sine. The derivative of negative sine is negative cosine. The chain rule brought out that square root 2 times. So what I get is what I want. I get something which, when I differentiate it 2 times, I get itself back times negative k over m. That, I know I just went fast, but if you slowly check the check that I just did, you'll see that this expression does meet the check. The other one did not. This one does. This is the solution to the differential equation. Where did I get the guess from in the first place? I'll explain that Wednesday. But the first thing I want you to see is that solving differential equations is reverse engineering. You come up with a guess and then you check the guess by differentiating. That's it. I know it. Oh yeah, you have to go. Okay, but have a great day. Thank you for waiting over a minute. I mean, and if there's any questions right now, I'll answer them. But thank you. You guys have been very patient. I think we got somewhere. Thank you.
Have a
Yes.
good day, Professor.
Thank you, Nicholas. Thank you. And thank you for showing video. Thank you all. Thank you. Awesome. Okay, great. Goodbye.